Sure. Don't worry, you take your own time.
So you would have about 45 to 50 minutes. Will that be fine, sir?
Yes. Around 40-45 minutes or so.
Okay.
And then if the participants are interested, we can have our discussion also.
Sure. I'm sure there would be some very interesting questions. I mean, this is the first time we are doing such a subject that we also do not have any expertise in. But in the last few sessions, we have found some very interesting questions, some challenging questions coming up. So we hope that we'll continue with that.
Right.
Sandeepan, is my voice clear with the mic over here?
Yes.
So we can start, I think, just turn 4, if that's okay.
Yes, I think we can start.
Wait a little bit. Let's wait a bit.
Hello, everyone. I would like to welcome you to the third session in our ongoing lecture series on science and technology in agriculture in India. The series has been organized by the Foundation for Agrarian Studies in collaboration with Rosa Luxemburg Stiftung South Asia. Through these 4-week sessions, we hope to expand the understanding of various developments in agricultural science that change the position of India globally in terms of food security, food sovereignty, and with regards to the country's capacity for innovating new technologies and utilizing them for agricultural production. You can find the inaugural lecture of this series delivered by Professor R. Ramkumar from the School of Development Studies at the Tata Institute of Social Sciences in Mumbai, and the first 2 sessions of this series on seed science and transgenic technology, respectively, on our YouTube channel. The link we will post in the Zoom chat on your right. We are glad to welcome Dr. Himanshu Pathak, Director of the National Institute of Abiotic Stress Management, who will be delivering a lecture on soil management for abiotic stress mitigation. If you have any questions for our speaker, kindly leave them in the Q&A box below, and they will be addressed in the last segment of the lecture. I would now like to call upon Dr. Sandeepan Bakshi, the Director of the Foundation for Agrarian Studies, to further introduce Dr. Pathak and begin the proceedings. Thank you.
Thank you, Mihira, and welcome all on behalf of the Foundation for Agrarian Studies. I welcome all to the third lecture of the series, as Mihira was mentioning, on the science and technology in agriculture in India. The purpose of this lecture series, as we have been saying, is to familiarize the students and scholars from the social science community to the component parts of agriculture science, the basics of their functionings, the various milestones in the development of agriculture science, and the effect it has had on agriculture production and agricultural economy in past, and the role it will continue to play in order to deal with future challenges. These lectures, we understand, will help us enlightening the debates around the use of science and technology in agriculture. This is not an exhaustive lecture series, and we will continue to expand our efforts to understand the other components of modern agriculture science and technology in the coming period, in the next few months. This series, you will recall, began with an inaugural lecture that discussed the long trajectory of the development of agriculture science and research in India, from the British colonial period till the current political economic context defined as neoliberalism. What were the major milestones that we achieved in this long journey, and the impact of these achievements on agricultural production and productivity? These were some points that were dealt with by Professor R. Ramakumar in his inaugural lecture. The lecture also laid the ground for a critical discussion on some very common, may I say, often misguided apprehensions about the use of modern science and technology in agriculture with respect to its impact on environment and on health. Some of these concerns are well-meaning, but the solutions often offered are based on unscientific approaches. That lecture laid emphasis on the need for maintaining a clear distinction between scientific research and technological advancement, and the question of who owns them. the opposition to private profits in the area of scientific research should not imply an opposition to the technology itself. Certainly, a message for us in the social science community. His lecture was followed by a lecture by Dr. Rajendra Prasad, the Vice Chancellor of the University of Agriculture Sciences, Bangalore. His lecture dealt with aspects of the application of seed science and technology. Following him, Dr. K.C. Bansal deliberated upon the evolution of gene technology, transgenics, and gene editing, how this science often mimics and helps in accelerating the process of natural evolution. Continuing with the distinguished line of speakers, today we have with us a renowned social scientist, Dr. Himanshu Pathak. Dr. Himanshu is the director of the ICAR National Institute of Abiotic Stress Management in Baramati, Maharashtra. He has previously served as the director of ICAR National Rice Research Institute in Cuttack, in Odisha. Previous to that, he was the principal scientist and professor at IARI New Delhi and was a joint facilitator of the Rice Wheat Consortium in New Delhi. He has also served as a visiting scientist at the University, at the Institute of Meteorology and Climate Research, Germany, and University of Essex, United Kingdom. Dr. Pathak's span of research includes soil science, climate change, and abiotic stress management. He was the lead author of the IPCC Fifth Assessment Report, and he was also part of the refinement to the IPCC guidelines for national greenhouse gas inventories. He is a fellow at the Indian National Science Academy, National Academy of Science, and National Academy of Agriculture Science, and many other such very renowned academies in India and abroad. His credentials speak for his contributions, and I do not want to take any more time of his. Without further ado, let me call upon Dr. Pathak. Thank you, sir, for taking out some time from your busy schedule. We are all eager to learn from you, and may I now request you to start your deliberation. Dr. Pathak.
Thank you very much, Mr. Bakshi, Ms. Nehira, and all the participants who are attending this particular talk. As suggested by Mr. Sandipan, I will be making a presentation on soil management for abiotic stress mitigation. Friends, I was really happy to know that there are already presentations made by Dr. K.C. Bansal and Dr. Rajendra Prasad, Dr. Ramanand of the inaugural address, and they are already have been through to some of the developments of agricultural sciences. Today I will be talking more about the abiotic stresses, its mitigation, its adaptation, particularly with some emphasis on soil management. Before I start, let me tell you, though the topic is abiotic stress, but there should not be any stress in you. We are not going to discuss anything which will be increasing your stress. I was told that there is already some rain is going on in Bangalore, so probably some of you might be already under some stress. So I'm not going to discuss any kinds of those difficult kinds of things. Very simply, in a very easy way, we shall try to understand what are these abiotic stresses and how these stresses can be mitigated. Friends, before I go, let me define what the stress means. It has got different meanings in different subjects. I'm sure all of you have studied in your class 10 or 11, 12, that in physical meaning, physically stress is a force per unit area, if you remember those classes of physical sciences. Chemically, stress is a trigger that alters a particular process, chemical process. Biologically, a stimulus affecting growth of organism, and that's what the stress is. And of course, psychologically, I shall not explain what psychologically stress means. Every one of us at some point of the time can be in some kind of stress. And that's how stress is defined in different subjects. But when we discuss about stress in agriculture, we generally talk of two kinds of stresses. One is abiotic stress. Abiotic stress are those stresses which are generated due to some physical or chemical factor. So physical or chemical factors will give rise to abiotic stresses. And there is another stress called biotic stresses, which is due to biological factors like insect, pest, diseases, nematode, bacteria, fungus. All of those come under biotic stresses. We shall not discuss those biotic stresses today. We will be discussing only on abiotic stresses. And whenever these abiotic stresses affect the plant, it affects plant processes, soil processes, water processes, as well as microbial processes. So all of these are affected by the abiotic stresses. I shall just give you one simple example. You can see this particular diagram. Let me show it once again. So there is rain or sufficient amount of moisture, but once the rain stops or it gets limited, you can see in the below one that the moisture of the soil is getting eroded and eroded and depleted. Once it is depleted and rain stops and you do not give any irrigation or water, then the plants will be in stress. Slowly, the leaves will be folding, and then after a point of time, it will be wilted. And even then, if you cannot provide water or irrigation, the plants will die. So this is what the stress does to a plant. Not only this water stress or moisture stress, which can be due to drought, scarcity of water, or flood, excess of water, but stresses could arise also from nutrient deficiency as well as toxicity, radiation, maybe high radiation, solar radiation or low solar radiation, or even lightning. It could be due to high temperature or low temperature. It could be due to pollution, chemical pollution, physical pollution, microbial pollution. It could be excess of salinity, alkalinity, or acidity, or sometimes it could also be mechanical. Mechanical means there could be due to wind, hailstorm, compaction, and so on. So it is not only related to water, but any of the factors, physical or chemical, if they are in excess or even if they are in limited condition, they will generate some kind of stress in a plant. And whenever stress comes, all these abiotic stresses, there will be several impacts, there are several effects within the plant. Their plant will respond in different way. But one thing, if you all can understand, the photosynthetic activity. Photosynthesis, all of you know, I shall just come to that one in a second. The photosynthetic activity of the plant will be reduced and plant growth will be retarded, and ultimately we will get less yield. So the crop yield will be reduced because of abiotic stresses. Now, how all of these things happen? I shall request all of you to remember what you have studied maybe in class 7, 8, or 9, the process of photosynthesis. The process, or probably the only process in the universe which can capture solar energy and converts that solar energy into chemical energy. So solar energy is converted into chemical energy in the form of sugar, C6H12O6, or carbohydrate. But this particular process of capturing solar energy into chemical energy of sugar is controlled or driven by several abiotic factors like solar radiation, which is very, very important, air, particularly carbon dioxide in the atmosphere, water, and of course the soil, which is the storehouse of all the nutrients, providing nourishment, water, and so on. So all of these factors, whether it is sun, air, water, or soil, will be dictating what is going to be the rate of photosynthesis and what is going to be the crop yield. You also should remember another process which is opposite to photosynthesis. We call that process as respiration. By the process of respiration, that sugar is broken down again to water and oxygen, and plants get energy. And we also get all our food and other requirement only from that particular process of photosynthesis. So what I was trying to convey you that this biotic process of agriculture, which is photosynthesis, that's a biotic process, that is a biological process. That biological process of photosynthesis is actually governed by several abiotic factors like sun, air, water, soil, and few more. And that's what gives to photosynthesis, and that's what we call as agriculture. And this is agriculture which gives us food, fodder, fuel, fertilizer, and fiber. All of these things, or all of these societal needs, food, fodder, fuel, fertilizer, fiber, directly or indirectly comes through agriculture, and again going one step backward by the process of photosynthesis. So that's the importance of this one. But friends, unfortunately, all these abiotic factors, whether it is water, soil, air, or space, are not in optimum condition or not in balanced condition. If these are in balanced condition, then there will be perfect photosynthesis and crop yield will be really very, very high, very, very good. But if any one of these abiotic factors, जो हम हिंदी में बोलते हैं आकाश, वायु, पृथ्वी, जल, ये अगर अग्नि, if these are not in balanced condition, optimum condition, then the plants will be experiencing stress. And once plants experience stress, the crop yield is going to be affected. Now, it is not that the stress is happening only last few years or last few decades. It is an age-old process. The very first day when agriculture or systematic crop production started, people say it was around 10,000 years back when systematic agriculture started. And from that day onwards, farmers have experienced abiotic stress in one form or the other. These stresses, as I mentioned, are very common and very frequent. It is not very unknown or very uncommon. Sometimes these are very extensive. The whole region, whole state, maybe the whole country is affected. And sometimes these are very intensive also. So these are extensive as well as intensive. These are very long lasting and expensive. The whole crop can die. The farmer will lose each and every penny of their only one source of income, that is agriculture. And the impact will not be for one season or 1 year. It could last for many, many years. These are very old, as I said, starting from the beginning of agriculture, very influential, very alarming, as well as very crucial. So friends, those who are related or connected directly or indirectly with agriculture, and if any one of you are coming from a farming family like me, you will all appreciate this statement that the farmers are born, they live, and they die with abiotic stresses. So this is their permanent companion. They experience abiotic stresses almost on a daily or seasonal basis. But unfortunately, because of some changes, these abiotic stresses are intensifying. There should not be any stress in optimum condition. Even if it is there, it should be minimum, but these are not in minimum, these are not in optimum, rather these are intensifying. Intensifying or aggravating because of climate change. All of you know that the temperature is going to cross 1.5 degrees centigrade line by 2040. I shall tell a little bit more about it. Water stress is increasing because of depleting groundwater, drainage problem, and so on. Soil quality is also declining. Nutrient deficiency is increasing. Pollution, air pollution in particular, and water pollution and soil pollution also are accelerating. And when some kinds of pandemic like COVID-19 and national lockdown comes, again, the stresses intensify. But more worrisome is that the projection, whether the projection by IPCC, Intergovernmental Panel on Climate Change, or our own agencies in our country, like India Meteorological Department, they say that the climatic extremes like cyclone, heavy rain, heat wave, flood, drought, all of these are going to intensify with more frequency. And that is the point of concern. So these stresses are going to intensify. These stresses are going to be more and more frequent. And all of these will be having their impacts on agriculture. Maybe 1 or 2 slides on climate change. All of you know about it. You know the IPCC 6th assessment report, the latest one, has been released on August 9, 2021, this year. And in that particular report, it has been mentioned that the climate change is widespread, rapid, and intensifying. And it will cross, as I said, 1.5 degrees Celsius line by not by the end of this century, but in next around 15-20 years by 2040. That's what the projection of IPCC was. And very recently concluded, I think few days back, the COP, Conference of Parties 26, which was happening in Glasgow in UK, the United Nations Secretary General said on November 1st in 2021 that either we stop the climate change, either we stop it or climate change will stop us. Either we stop it or it will stop us. And he said, this is the time to say enough, enough. He also added that the addiction to fossil fuel is pushing humanity to the brink of collapse. So these are the grave concerns of climate change. And probably if you are following at least news channels, you will also know that Government of India, our Honorable Prime Minister, has also made several commitments to combat climate change. In COP26 in Glasgow, India committed 5 aspects which call 5 Panchamrit. Those are, by 2030, we are going to reduce emissions intensity by 45%. We are going to draw 50% of energy from renewable sources. We are going to raise non-fossil fuel-based energy capacity to 500 gigawatt, and we are going to cut carbon emission by 1 billion ton. And by 2070, India is going to attain a net zero emission and carbon neutrality. So there will be no net emission. Whatever we'll be emitting will also be consuming the same one. So with this background, let's go to the next part. What are the impacts of stresses, particularly abiotic stresses on agriculture? The impacts will come from some of the concerns. One is temperature increase. As you know, temperature is increasing because of climate change. Weather hazards, whether it is cyclone, whether it is hailstorm, whether it is flood, something like that. Sea level is also rising. I shall not go into details, but once it rises, the coastal area is going to be very, very severely affected. Droughts and floods, their frequency are increasing. And along with that, not in a very, very visible way, but there are several abiotic as well as biotic stresses which are intensifying almost in every field, every village. I shall just give one example of impacts of drought in agriculture. This is just one of the stresses, drought stress. As you know that out of 140 million hectare net sown area of our country, 75 million hectare is unirrigated, rain-fed. And these are the areas which are prone to drought. If the field is rain-fed, you do not have source of irrigation, then the field is prone to drought. Impact of severe droughts on India's GDP, gross domestic product, it is estimated to be around 2 to 5% per annum. Drought alone, 2 to 5% of GDP. And about 5 crore people are affected by drought annually. And if the drought becomes severe, then around 33 crores, 1/3 of our population will be affected. That is the estimation of Department of Agriculture and Cooperation and Farmers Welfare in just last year estimate. So these are the impacts of only one stress called drought. And that's why people are also saying that after this COVID pandemic, drought is going to be the next pandemic. And unfortunately, we do not have any vaccine for that one. Fortunately, we have got vaccine for COVID, but for drought, we do not have a vaccine, and we certainly need a vaccine for that. Just to give one more example about the cost of drought. In Maharashtra, we estimated that because of one season drought, the total loss will be around 22,000 crore rupees in Maharashtra alone. You can imagine if the calculation is done for the whole country for 1 or 2 consecutive years, then what could be the total volume of loss? Friends, the major concern of all these abiotic stresses are that the poor farmers, poor people are going to be worse sufferers, not the rich farmers, not the farmers who have got access to technology, who have got sufficient amount of resources to adapt. But the poor farmers who do not have sufficient technologies, they are going to suffer most because they depend more on stress-sensitive natural resources. They depend more on soil fertility. They depend more on natural water availability. and so on. And unfortunately, they do not contribute to any degradation. They do not pollute water. They do not emit carbon dioxide to cause global warming or climate change. But when the impacts come, they are the ones who are going to be most severely affected. Now, before I go to new technologies, let me tell you that in nature, there are already some kind of mechanisms by which an organism responds to stress. An organism responds to stress by several of the natural ways. One way is, of course, migration. Migration means moving away from the stressor. So if there is drought in one place, you move to another place. If there is flood in one place, you move to another place. If the temperature is more outside, you come inside in your AC room, and then the stress is gone. But this is for the human being. Plants cannot move. If there is drought, they have to be there. If there is flood, they have to be there. So migration is not an option for that. Second one is, of course, mitigation. Reduce or eliminate the stressor. I shall talk a little bit more about that. Adaptation, adjusting their growth and development to stresses. Transduction, transfer of genetic material from one to another. Probably Dr. Bansal might have covered a part of this thing. And of course, evolution, development of new form from the earlier form. Probably all of you remember the Darwin's theory of survival of the fittest, theory of evolution. Evolution of different organisms have happened because of some kind of stresses arising at that particular point of time. And you remember or study that particular sentence again, survival of the fittest. He didn't say that survival of the best or survival of the largest or survival of the smartest and so on. He said survival of the fittest. What does it mean? It means that particular organism which fit better in the changing scenario, that organism is going to survive. Not the largest one, not the smallest one, not the smartest one. So you have to fit with the new system, new temperature, new water, new climate, and so on. And then only you will survive. If you cannot fit, then you are not going to survive. So these are the natural ways of mitigating or responding to abiotic stresses. Now let's come to agriculture and then subsequently Indian agriculture. Friends, as I said, agriculture probably, systematic agriculture probably started around 10,000 years back. But of course, from the day of cavemen, now we have become a man or farmer like this, using all kinds of heavy machineries. It has not happened in one day. These are all the cycles. We started with the equipment, then we used animal power, then all kinds of development happened, and now we are using very heavy machineries of tractor, combine, and so on. And all this mechanization has really helped Indian agriculture. All the science and technological tools have really helped Indian agriculture. How it has helped? If you just see the numbers, the country, when it got independence in 1947, and these are some of the data after 3 years, 1950, 51. If you see that in terms of food grain production, vegetable, milk, egg, fish, all of these by the end of 2020 to 21 has increased several times. Food grain has increased by around 6 times, vegetable 13 times, milk production 11 times, egg production 50 times, fish production 17 times, and so on. Though the net sown area has remained more or less same, 130 in 1950 and only 140 in 2021. Gross sown area, of course, has increased a little bit, but that means that with using the same land, same net sown area of 140 million hectare, we have increased the production by 6 to 50 times. And you also know that in COVID situation, agriculture sector performed well. No other sector of Indian economy performed well. All were rather in collapsing mode, but agriculture was the one which performed well and had very good growth even during the pandemic. Friends, this was not the case earlier. Now we have got sufficient amount of food, but it was not the case of food history of India. Before 1947, Indian history was repeated with famine, drought, and food shortages, several of those. At least 20 million lives were lost in about 20 famines that have struck since 1850. And all of this, so India was a begging bowl till 1960s, but in 1960, Green Revolution came and then there was a big jump. All of you probably know about this particular term, ship to mouth, that India was living till 1965 as ship to mouth. We used to import lots of food from USA, which used to be distributed to different corners of the country, villages, cities, towns, and then only most of the Indians used to get food. And then, of course, there was a very good report by William and Paul Paddocks, America's Decision, Who Will Survive, which was submitted in 1967. And in that particular report, it was said that India is a country without any hope for agriculture, from agricultural front. Whatever food aid India gives, USA gives, India will not be able to survive, and India will never be in a position to produce sufficient amount of food by itself. But today this was proved to be wrong. Since from the day of our independence, our first Prime Minister, which said in our speech, India stressed to its destiny that everything else can wait, but agriculture. It's a very, very famous statement, and all kinds of policy decisions were taken from that particular time. And then, of course, in Green Revolution, these varieties, which we call as miracle varieties, this is a very, very important photograph. And I would request all of you to please see this photograph, not for its beauty, for its color, but only to see the variety which was developed IR8. And this is the miracle variety of rice, which totally changed the food scenario of the country. This particular variety was bred by crossing this one, Petra, and the dwarf variety DGOG, DGWG we call. By crossing these two, scientists developed the variety IR8. If the yield potential of these varieties used to be 2 tons or 3 tons, the yield potential of this variety IR8 was 10 tons per hectare. 10 tons per hectare. And this was the variety which was released in 1968 in our country, and that triggered the Green Revolution. And similar kinds of things happen in case of wheat. These are earlier very tall varieties of wheat. All the people are totally, they are not seen in the field, but then several new high-yielding varieties came, and because of all high-yielding varieties, the productivity of wheat, this is the one, you can see the structure of these varieties, productivity of wheat increased many folds. So whenever we talk of Green Revolution, very quickly, let me tell you, friends, it is not only science-driven, it was a very good synergy between science, policy, and farmers. And 6 names I would certainly request you to remember who were responsible for Green Revolution in our country. One is Norman Borlaug, who is known also as father of Green Revolution across the world. Srimati Indira Gandhi, our honorable Prime Minister of that time, and then 4 S. And this S stand for C. Subramaniam, who was Agriculture Minister of that time. Mr. Anna Sahib Shinde was Minister of State of Agriculture at that time. B. Shivaraman was the Secretary Agriculture of that time. And of course, Dr. M.S. Swaminathan, the Director of Indian Agriculture Research Institute, the institute where I did my master's and PhD. So they were the people who were responsible for Green Revolution in this country. And of course, when you talk of White Revolution in milk, that was also again a synergy between science, policy, and farmers. And who can forget the name of Dr. Verghese Kurian, who led the whole revolution, and today our country is self-sufficient in milk production. Not only Green Revolution in crop or White Revolution in milk, today we have got several other revolutions like blue, yellow, golden, silver, brown, or gray. I shall request all of you to go through the details of what these revolutions mean. So friends, to sum it up, the country was food scarce country till 1950. It was a food shortage country from 1950 to 1917. From 1970 to 2000, it was a food sufficient country. From 2000 to 2010, it was a food secure country. And 2010 onwards, it has become a food surplus country. So from scarce to shortage to sufficient to secure and then food surplus country we have become. But then it doesn't mean we do not have any kind of challenges. Rather, we have got more and more challenges. The challenges are to produce more food with less land, less water, less chemicals, less pollution, less global warming, and so on. Very importantly, we really need to increase the income of farmers. If you see this particular diagram, you will see that the monthly income of an Indian farmer is very small, around 6,000. Contribution of agriculture to gross domestic product of India is only 17%. In pandemic year, it was around 20%. But the population who are depending on agriculture is 55%. So that simply means that the contribution of non-agriculture sector to GDP is 83%, and population depending on that are 45%. So 45% people are using 83% of the GDP, and 55% of the people are using only 17% of the GDP. So that means the moment you say you are a farmer, your monthly income or annual income is certainly more than a non-farmer. So that's what it means. And of course, the land holding capacity is also increasing because of population is increasing. So this is going to be another challenge. Now, a little bit of soil, as myself a soil scientist. Friends, soil is not only a medium of growing plant. Besides the medium, besides providing nutrient, water, and several other things to plant, it also helps in conserving biodiversity, conserving biomass production, purifying air, purifying water, and also ultimately human health. So all these roles are played by soil. Soil is certainly important from our food and health point of view because healthy soil produces healthy food. Economically, it is important because healthy soil requires less external inputs like fertilizer, water. Environmentally, it is very important because healthy soil keeps environment healthy, water healthy, air healthy. And if the soil is sound, then probably we shall not be dependent on other countries for import. And generally, they say that if the soil is poor, the people utilizing that soil is also poor because of less productivity. You all know about Sustainable Development Goals, all 17 are there, and each and every Sustainable Development Goals are also directly or indirectly related to soil health. So generally, sometimes we say that Sustainable Development Goals can also be renamed as soil development goals. If the soil is not good, then probably you cannot achieve the Sustainable Development Goals. Of course, I shall not go into details, but very quickly, let me tell you, we are talking about soil health. Soil has got physical health, chemical health, and biological health, and all are very, very crucial for crop production. But unfortunately, soil health is going down because of inappropriate land use, because of deforestation, urbanization, water and wind erosion, faulty irrigation or agriculture management, dumping of waste, discharge of pollutants, mining of nutrients, depletion of soil carbon, and of course, climate change. All of these causes are degrading our soil resources. Some data, if you're interested, around 24% of global soils are degraded. In India, 121 million hectares, 36% of total geographical area of the country are also having some kind of degradation problem. And annually, if we calculate the loss, this is equivalent to 1.2 billion US dollar, $2 billion. These are also intensifying. Nutrient deficiency, as you know, are also going down because earlier only nitrogen was deficient, but now we can see not only nitrogen, but around 7 or 8 nutrients are also getting deficiency symptoms. Our aquifers are depleting. We are pumping more and more groundwater. And as a result, the aquifers, the groundwater level is going down. And you can see number of pumps we are putting. Each and every dot is equivalent to 1 pump. So you can calculate how many pumps are there to pump the groundwater. Pollution, unfortunately, in this country, almost all the water bodies, whether it is river water, whether it is lake water, sometimes even ocean water or sea water, are also polluted. Once these are polluted, and when you use this polluted water either for your own consumption or domestic use and also for agriculture, the stress is going to intensify. Water availability is also going to go down. Already India is a water stress country, but in next few decades probably India is going to be water scarce country, whether the availability of water will be less than 1000 meter cube per person per year. So these are the things. So with this kind of background of little bit of abiotic stresses, defining them, little bit what are the impacts of abiotic stresses, and also mentioning about the soil and its role in managing stresses and promoting agriculture, let me very briefly tell about what are the options to manage these abiotic stresses. And here will come the role of science and technology. But before, let me tell you, friends, we generally use two terms. One is adaptation and another one is mitigation. Adaptation means adjustment of your agriculture along with the stresses. So for adaptation, the crop has to be more resilient to heat, drought, flood, salinity, and pest, all those stresses which I was mentioning. And if you talk about soil, then the soil management should reduce the stress and enhance the resilience. And that's what we need to do over here. Second term is, of course, mitigation. And for mitigation, the crop has to be more efficient for water use, fertilizer use, and energy use. And soil management should enhance the efficiency and reduce the emission. So these are the two general terms we use, adaptation and mitigation, and how soil management can help in both of these processes. Generally, we use the term or strategies called 3A strategies to manage abiotic stresses. One is avoid. Avoid. Do not grow a sensitive crop in the stressed region. Or adopt. Use technologies to reduce the stress on crop. Or alleviate. Use technologies to reduce the stress from crop. Sometimes crops also give stress to soil and water. So do something so that you will be able to alleviate the stresses from coming from agriculture. I, 2 years back, proposed a farm building approach. What is farm building approach to manage abiotic stresses? If you want to manage abiotic stresses, the first step you should do is foresee the stress, which we call as forecasting. Second one is adapt the stress, adjust your agriculture, adapting. Third one is responding to the stress. Fourth one is mitigate the stress. And fifth one is build capacity to manage the stress. So foresee, adapt, respond, mitigate, and build capacity. Farm building is the one which we should do for managing abiotic stresses. Now let me very briefly show you what are those solutions or tools to manage abiotic stresses. Broadly two. One is go for stress-tolerant crop varieties or animal breeds if you are in livestock sector. And second one is stress-tolerant management practices. So stress-tolerance cultivars or breeds. And second one is stress-tolerance management practices. Fortunately, our country has got several climate-smart stress-tolerant crop varieties for every crop, whether it is rice, wheat, maize. Indian Council of Agriculture Research, in which I work, more than 100 varieties of different crops have been released, which are tolerant to several kinds of stresses like submergence, drought, salinity, as well as biotic stresses. If you want, probably we shall discuss more about it in our question answer session. Besides developing new stress-tolerant crops, we are also promoting some new crops which were generally not grown earlier. One, that kind of crop is called dragon fruit. This is a picture of our own institute, Niazam Baramati, where a very successful production of dragon fruit is going on. This is a cactus type of plant. It doesn't need much water. It doesn't need even good soil. It doesn't need much care also. So all the degraded lands of the country can be used for growing crops like dragon fruit, quinoa, chia, and so on. And these are called stress-tolerant, climate-resilient crops. And these are the crops which can bring very good price for the farmers in the market. Dragon fruit is one of the costliest fruit marketed in the country as of today. Second one is, of course, using the tools of plant breeding. including biotechnology, molecular biology, genome editing, and so on. I shall not go into details because I am sure Dr. Bansal has covered this particular thing. Only again to remind you that what we do in those kinds of new tools and techniques of plant breeding, that we can combine the traits which provide the tolerance to several stresses. For example, high root density is one trait which gives the capacity of a plant to tolerate drought. Similarly, stay green, the plant will remain green so that photosynthesis will continue for a long time. So this is another way. So if you can combine these two, stay green quality, a trait with high root capacity, then you get a plant which is stay green, high root, and that's a plant which will give drought tolerance and also good yield. So this is basic one. Here I am saying only two traits have been combined, but using several other new tools, not only two or three, several of the traits can be added or pyramided. So trait 1, trait 2, trait 3, you can combine several of these traits using modern tools of molecular biology, and then you can develop a variety of your choice, which will be high yielding, which will be of good quality, and at the same time, it will be tolerant to several abiotic stresses. Another technique which we are working in our own institute is to combine rootstock and scion of different varieties. Some of the varieties where rootstock is tolerant to stresses of salinity, drought, and so on. So we put that rootstock, and then above that we put a scion, which is of popular, good quality, high yielding variety. So when you put them together, then you get a plant which are of again high quality, high production, but tolerant to drought and some other abiotic stresses. So we are already working on tomato, capsicum, brinjal, and so on. Next will be management aspect, and there water management is very, very crucial. Water management is very, very crucial. We all the time say now let us not go for flood irrigation, we should go for the irrigation practices like drip or sprinkler, or using some kind of sensors labeling your field so that you need less and less water. Similarly, in the front of nutrient management, fertilizer management, several new developments have taken place. Probably all of you know that since last few years, all the urea, 100% of urea which is used in our country are now neem coated. What does this neem coating does? Neem coating enhances the efficiency of urea fertilizer by around 5 to 10%, and it also reduces the emission of greenhouse gases from fertilizer application. So this is from the nutrient point of view. You also probably know that very recently nano urea, nano fertilizer has already been started operational, and this nano fertilizer is another very good product which can enhance the efficiency of nitrogen fertilizer by around 10 to 15%. Then again, you know probably soil health card program of Government of India, that every farmer fields soil has been tested and a card has been given to them. That card tells you what is the health condition of the soil and what kind of fertilizer, how much of it should be used to get a good yield in that particular soil. So when we combine all of these, combining soil, water, and nutrient management practices, then we are certainly going to get tolerance to abiotic stresses. Now, let me also tell that there are some opportunities. Those stresses are going to affect yield, it is going to reduce yield, but still there are opportunities. One opportunity is in our country, there is still a long yield gap. What is yield gap? Yield gap is the gap between the potential yield, how much yield you can get with a particular variety, and what actually you are getting. For example, I was talking of IR8 variety, and there are now several very good varieties of crop, rice, wheat, and every crop. So for example, with good management, if the variety can give you around 8 tons per hectare, and currently farmer is getting only 3 or 4 tons per hectare, that means there is gap of around 50 to 60%. If this gap can be bridged, if this gap can be narrowed down, then the total production of the country can be increased. So there is still a long opportunity, very large opportunity to increase the yield of almost all the crops because the gap is very high. Second one is whatever technologies we have got, including new fertilizer, new irrigation, new soil management, new varieties, and so on. If we adapt or if we implement, if farmers start practicing those technologies, then as I was saying that if this is the baseline, you will be able to increase your yield. So whatever yield is going to be reduced because of abiotic stresses or climate change, those yield loss can be compensated. And not only it will be compensated, rather it is going to be further enhanced by the implementation and adoption of some of the new technologies. So friends, with this, some background about abiotic stresses, its impacts on crop productivity, and what are the technologies available, including soil, water, nutrient management, and new varieties. So what could be our way forward to manage abiotic stresses? One, I would certainly say, first one could be eco-regional agricultural planning. What is eco-regional planning? Eco-regional planning means we should grow a crop in that particular area which is suitable for its growing condition. For example, rice growing needs a lot of water. It needs a clay soil, heavy soil, where percolation or movement of water is less. So we should be growing rice in those areas where rainfall is more, soil is clay. This is one assessment we did, and there are some very good publications on this, that all these green and blue and yellow areas are the areas in the country which are suitable, very suitable, or moderately suitable for growing rice. If we grow rice in these areas, we will require less amount of irrigation. We would require less amount of fertilizer as well. But if you grow rice in the unsuitable areas, which we are doing at present, then we are going to face more and more stresses and going to use more and more water, which will be causing depletion of groundwater, fertilizer pollution, climate change, and so on. Second one is, of course, as many of you can understand very well, reducing food loss. You'll be astonished to know that whatever food we produce globally, and that is around 2,700 million tons, 36% of that feed goes for animal feed, 47% used as food for people, 5% goes for biofuel, and 12% for others. But the unfortunate part is 1/3 of the food produced globally is lost. In our country, around 20%, and now it is increasing because we do not have storage capacity. A very large amount of food is lost. So why to produce food when it is going to be lost? So the management should be, of course, to increase food production, but more should be to reduce the loss. There is no point of producing and then getting it lost by various processes. So this is certainly number two. Number three, from a biotic stress point of view, is choosing local and seasonal food. If you do that, then probably you will be able to utilize it locally without having implication on abiotic stresses or climate change and so on. Growing food locally could be another option. And finally, using emerging science and technology. When I talk of science of technology, very, very new technologies are coming, starting from your drone. Now, drone has been started using in agriculture for mapping, for application of pesticides and several other operations, use of solar energy, use of simulation models, use of drip, sprinkler, and so on. And all of this, starting from high-yielding stress-tolerant varieties, I gave you a few examples, automation and mechanization for our tillage and farm operations, efficient need-based input use like water as well as fertilizer, and then also integrated it with livestock and fisheries. And in each and every area, there are some very good technologies available and many more things are evolving. So certainly we need to use all of these technologies to make Indian agriculture free from the abiotic stresses. But in spite of having all these technologies, what I say all the time, that there are 5 aims for stress-smart agriculture, particularly Indian agriculture. And if we do not have the access to these 5 aims, then certainly we will not be able to make Indian agriculture stress-smart. What are those aims? Market, very important. Market, monsoon, mechanization, management, and mainstreaming. So all these 5, besides science and technology, need to be putting together to make Indian agriculture stress-smart. Friends, up to 1950, we had our traditional farming. Then we had mechanization in 60s, green revolution, late 60s and 70s, biotechnologies in this new century. And then, of course, precision agriculture, where water management, nutrient management, soil management should be done very, very precisely. And that's how it is going to be making Indian agriculture free from abiotic stresses. This is my concluding slide, friends. I want to conclude with some kind of philosophical, but also in a realistic way of how to make Indian agriculture tolerant to abiotic stresses. Friends, you all will agree with me that all the developed countries of today, Europe, Australia, US, and so on, around 50 years back, their economy was more or less the economies of our country of today. Not exactly, but more or less. But these developed countries of today, from developing country 50 years back, so from there they have gone to become developed countries. But after becoming developed countries using all the fossil fuel and energy and more of water and nutrient, now they realize that their development is not climate friendly or stress friendly development. So from this particular point, they want to go to this particular point to make their development climate friendly or environment friendly. We are still here. What we are trying, that we are also trying to go from this particular point to that particular point, and from there we shall again go to this particular point. But instead of doing that, we should be following this particular path. Because all of you know in geometry that the length of this side is always less than the sum of the other two sides of a triangle. And this is the path of which you call as path of low carbon, low water, low nitrogen, and low energy. And if you can go with this low energy path, then agriculture is going to be climate friendly, environment friendly, and free from abiotic stresses. But the problem is when you go with that, the profit also becomes less, and then people are generally not interested. So friends, let me conclude. Firstly, that people are dependent on soil and agriculture, as I said, and soil or agriculture also depends on people, poor soil, poor people. Abiotic stresses are intensifying with climate change and natural resource degradation. I explained to you. There are threats of degradation, pollution, and climate change, and which are getting more intense, more alarming. Sustainable soil management is crucial, but we need to understand the plant-soil interactions in response to abiotic stresses, and for that we need science-backed policy for production, procurement, processing, and promotion to get the or to reach the benefits to the farmers. And that's what we need to do now. With this, I thank each and every one of you for giving me this exceptional opportunity to discuss with all of you about abiotic stress management in agriculture, what are the consequences of abiotic stresses, and how the new tools and techniques in agriculture, particularly in the form of soil, water, and nutrient management, can help Indian agriculture, climate smart, can help Indian agriculture to become tolerant to abiotic stresses. Thank you very much. Thank you all for this wonderful opportunity. Thank you very much.
Thank you, Dr. Himanshu Pathak. Many thanks for that extensive sweet discussing the different kinds of abiotic stress, particularly in the context of climate change, and how through sustainable input management, in sustainable and integrated input management, including soil management and science-backed policy framework, we can efficiently deal with different aspects of abiotic stresses that you had explained. We have about 15-20 minutes for question answer and a round of discussion. So may I request the participants to please type in your questions in the chat box or the Q&A box, or if you have any comments, you can please feel free to put those comments as well. While we wait for the questions, maybe in a couple of minutes we expect some questions to come in. In the meanwhile, Dr. Pathak, may I ask, put forward a point that we see in the social science and among the students and scholars in the from the social science, social scientists and students of social science, that there are a lot of apprehensions about the use of modern science and technology in agriculture with respect to its impact on environment and health. So in the wake of the discussions on climate change that you just ended with, we often also find an emphasis on more towards nature-based solutions, or maybe also traditional ways and methods of cultivation, pitching them against a more science-based approach, something that you were deliberating upon. So we would like to understand a little bit your views on this. Is that, is the conflict that is being that is often playing in the minds of students and young scholars such as us, what would be your response to it while we wait
Right,
for the
right,
question?
right. Thank you very much. May I respond now?
Yes, please.
Yeah. Okay. Thank you very much. Let me tell you in a very simple way that if you use, or if you are intended to use only natural based processes without putting any new technology, without putting any external resources like fertilizer or water, the crop yield on an average, say yield of rice or wheat, is going to be 2 tons per hectare. Without putting any fertilizer, without putting any water, generally field will provide you around 2 tons per hectare. Now, 2 tons per hectare yield is not sufficient in today's context to feed the population. We need at least 4 to 5 tons per hectare of yield. Now, if you have to harvest 4 to 5 tons per hectare of yield, then certainly relying totally on the nature, totally on natural resources, totally relying on rainfall and everything, it is not going to be possible. Without new science, new technology, new tools and inputs outside fertilizer, irrigation, pesticides, your yield cannot be increased from 2 tons roughly to 4 tons, 5 tons, or even more than that one. Now you have to make a compromise there. Are you satisfied with only 2 tons per hectare? If you are sufficient with 2 tons per hectare, then probably we can go ahead with all the natural processes without any fertilizer or irrigation. But certainly not. The population is there. We have to feed them. Their demands are also increasing. It is not only the food requirement is increasing. It is not that only rice and wheat requirement is increasing. The quality, now they want better quality. Not only better quality, now also they want different kinds of foods. Probably you remember earlier, my father or my grandfather used to be very happy if they used to get 2 times chapati and chawal and roti. But now we need egg, we need milk, we need chicken, we need mutton and all of these things. Then if we have to provide all of these, we have to increase production. We have to have the technology of new science and new tools and techniques. So that's the easy way to understand. And there you have to make a compromise. And choice is, of course, yours, the way you want to take a decision on this.
Okay, thank you, sir. I somehow want to probe on why are you using the term compromise there, but let me not take any further time at this moment and look at some other questions that have come. We have 2 questions. The first says, are we seeing large yield gaps because of increased abiotic stresses or due to lack of scientific farm management? Do we have any studies that quantifies the contribution of these 2 factors?
Yeah. Right. Let me again define the achievable yield. The achievable yield is the yield when you provide all the requirement. You provide good amount of water, sufficient amount of nutrients, sufficient amount of pest control. Then whatever yield you get is the achievable yield or potential yield. Now, and if you do that, probably you are going to get, say, 6 tons per hectare yield. But what farmers are getting is only, say, 3 tons or 4 tons. So this particular gap is because there is some kind of deficiency of water or nutrient or some kind of pest and diseases. And these are the stresses. So these stresses are reducing the yield. What new tools and new science and new techniques will do, this will give you the ways, mechanisms, the tools and inputs which will reduce these abiotic stresses. And once you reduce the abiotic stresses, your yield is going to increase from, say, 3 tons to 4 tons to 5 tons. So the role of the tools and techniques, inputs and new science is to reduce the stress so that whatever yield you are getting now, 2 tons or 3 tons, can be increased to 4 tons, 5 tons, 6 tons, and so on. So that's how the relationship is.
Okay, so Further, there is a question which says, can you please give some Indian examples related to rice research where we have combined both resilience to abiotic stress and also increased yield?
Very good. There are very good examples of two or three. In say Eastern India, earlier we used to grow tall varieties where the yield was maximum around 2 to 3.3 tons per acre. Now, in 2016, and let me tell you, I was also director of that Rice Institute for 3.5 years. We released two varieties, CR Dhan 801 and CR Dhan 802. These two varieties are high yielding. They can give around 8 tons per hectare yield, but at the same time, they can tolerate to flooding as well as drought. Tolerant to flooding means, let me explain what this flooding tolerance means. The ordinary varieties of rice, if the whole plant or whole rice plants are under water for more than 6 days, and then after 7 days the water goes down, then you are not going to get a single grain of yield. So maximum 6 to 7 days submergence, an ordinary rice variety can tolerate. Now these varieties, Siardhan 801 and 802, even if the whole plant is under water for 17 days, and after 17 days water goes out, then also you are going to get, of course, not 6 tons per hectare or 7 tons per hectare, but you are going to get around 4 to 4.5 tons per hectare. Had it been only other ordinary variety, you would get almost nil. So this is one specific example of submergence tolerant, and these are also tolerant to drought. Ordinary varieties can tolerate only maximum 10 or 12 days of water scarcity, but these varieties can tolerate up to 20 to 25 days. So this is a very good example, and not only these two, there are several other examples also where high yielding and stress tolerance, whether it is submergence or drought or even salinity, have been combined to get out of these abiotic stress tolerance problems. And those who want to know more about it, probably they can visit the NRI website where the details of these varieties and few others, as also the website of IARI, Indian Agriculture Research Institute, and many other institutes where the details of these varieties and their properties, their traits are explained very well.
Okay, we have a few more questions.
Go ahead,
Yeah. Professor Ramkumar, one second. Yeah. Okay, so we have one question from Professor R. Ramakumar who asks, who says, a commonly held view among a few is that soil already has all the nutrients needed for the crop, and you only need to, intermediate their availability to the plants using, cow dung or cow urine or some sort of proponents of method like ZBNF would say. Is that, this is a view among a few, and we would like to know your views in this regard. We would like to understand.
Very good question. When soil science research started, say around 150 or 200 years back, before that, the view was that soil is a nutrient bin, and soil can supply enormous amount of nutrient to plant for very, very long time. Let me give you one example. If you are harvesting around 5 tons of rice per hectare, or say 5 tons of wheat per hectare, that particular crop needs around 100 kg nitrogen, around 20 kg phosphorus, and around 120 kg of potassium. Just giving example of NPK. These are the largest quantity of nutrients which plants need. If the soil is not cultivated earlier, it has been simply started from forest, and then now we have started cultivating. For 2-3 years, that particular soil will be able to provide the sufficient amount of N, P, and K. But then if you continue growing rice and wheat and some of the other, or any other crop except legumes, for example, probably the soil, not probably, for sure the soil will not be able to provide that 100 kg and 120 kg of nitrogen and potassium, and the crop yield is going to go down. So that means if you have to harvest that 5 tons per hectare rice or wheat every year, then the amount of nutrient which the crop is taking out of the soil, you have to supply back it to the soil. And this is actually the first law of agriculture. This law is called as law of restitution. Law of restitution means whatever the plant is taking out of soil, you have to give it back to the soil, then only the soil will be in a position to supply sufficient amount of nutrient for good yield. Now, naturally, potassium is not added by any other natural processes. None, no one. Phosphorus is not added by any natural processes. Nitrogen is done by biological nitrogen fixation, but unfortunately that capacity is given only to the legumes like pulses and so on. Rice doesn't have that capacity. Wheat doesn't have that capacity. Yes, soil can do that, but that quantity is only 5 to 10 kg per hectare, maximum 20 kg. But as I said, the crop needs 100 kg of nitrogen. So the point is, if you do not apply fertilizer, the soil will not be in a position to provide 100 kg or 120 kg of nitrogen or potassium for a long time. It will be exhausted. It will be exhausted within few years, and then you will again start getting only 2 tons, 1.5 tons, and so on. So the point is, soil cannot supply sufficient quantity of nutrient for a long time. You have to apply either manure or fertilizer or whatever it is, so that the continuity of supply from soil will be maintained and crop yield will be similar as every year. But without that, no. You will get yield, but it will be only 1 ton or 2 tons per hectare. That's what it is.
Thank you. Thank you, Dr. Pathak. That was, I think that was a much needed clarification, and thank you for being so direct with that.
Right.
Madhura Swaminathan asks, can you give an example of recent technological development in respect of adaptation to soil stress?
Yeah.
One
very good example which we are trying for last several years, we call it conservation agriculture. In conservation agriculture, we are generally trying to do 3 things. One is to reduce number of tillage, because you till the more, then the soil organic carbon is exposed to sunlight and temperature, and carbon dioxide is lost. Second one is covering the soil with crop residues. You know, lots of crop residues are burned like Punjab, Haryana, so cover the soil with crop residues. And third one is to grow legume. So this is called conservation agriculture. And if you follow all these things, you will be able to maintain soil organic carbon, also modulate soil temperature, and several other benefits, so that the crop will be having better condition to grow. And this is only one example. Other new sophisticated tools are in the form of nutrient management, as I said, new form of like nano urea or an imported urea, water management like drip irrigation or sprinkler irrigation. Now we are trying with subsurface drip irrigation also. The pipes are put so that if you go for flood irrigation, then your efficiency is only 35 to 40%. Around 60% water is lost. But if you go for drip irrigation, then the efficiency of water is around 75 to 80%. So with less amount of water, you can get similar yield or even sometimes higher yield. So every front, whether it is soil management or water management or even nutrient management, there are some new tools and techniques which gives adaptation benefit to the crop. These are there, and fortunately, a large number of farmers are already adapting it. Not every farmer of the country, unfortunately. For example, in Maharashtra, probably many of you have seen the area where I am working now, almost every field is having drip irrigation system. There is flood irrigation almost non-existing. But if you go to other parts of the country, then of course flood irrigation is the one which is very commonly practiced. 90% areas are flood irrigated. So this is something which we now need to adapt to have more benefit out of the very limited amount of water or nutrient which we have got with us.
Thank you, sir. We have a question from Dr. Suresh. Dr. Suresh is a long-standing collaborator, and let me humbly say that he was supposed to moderate this question-answer session, and but he had another prior commitment. He tried to sort of work around that, but unfortunately, that could not happen. So, but I'm very happy that he could eventually join the today's session. He asks that is there any possibility of reducing chemical fertilizer in Indian agriculture without compromising food production? And if so, what could be the range of reduction in fertilizer use?
Right.
Yes, sir.
Again, very good question. I was telling about the efficiency of water, 35%. Unfortunately, the efficiency of nitrogen fertilizer, for example, is also 35%. What does it mean? It means that if you are applying 100 kg nitrogen, only 35 kg is taken up by the crop. Remaining 65 kg is lost in the process, lost from soil, lost by water, and so on. Now, if we can increase the efficiency from 35 to 45 or 50, 55, then proportionately you can reduce the amount of fertilizer. More efficiency, less loss, less amount of fertilizer. That's very simple equation. Now the point is how to increase the efficiency. One is use of neem-coated urea. Thereby we are already increasing efficiency by around 5%, sometimes even 10%. Second one is use of now nano urea, could be again contributing to 5% or so. And then very importantly is fertigation. Fertigation means applying fertilizer or nutrient along with water, particularly drip water. As you know, in drip water, we apply that much of water which is just required for the plant in the root zone. And along with that water, nutrient is also added. So the nutrient which is added exactly in the root zone, that will be directly taken up by the crop, and by doing that, efficiency will increase from 35% to sometimes 65% or 70%. So if it happens, proportionately the amount of fertilizer requirement also could be reduced. Our target of Government of India is that in next 10-15 years, the fertilizer consumption, particularly nitrogen fertilizer consumption, should be reduced by around 25%. This is one. Second one is, besides fertilizer, which supplies, say, nitrogen or phosphorus, there are several organic sources which also should be utilized properly to supplement good amount of fertilizer, like crop residues, like compost, like farmer manure, like any other organic matter, even coming from factories and so on. If we can properly collect, process, and apply those, then those will be very, very good sources of nutrients. And whatever you will be applying, a proportionate amount of fertilizer, chemical fertilizer application can be reduced. So there is good opportunity, good potential of utilizing these new sources as well as new technologies to reduce the amount of fertilizer which we are utilizing today in our agriculture system.
Okay, so we have three more questions, 3 or 4. I think that this is the last set of questions that we'll be able to take.
Okay.
The first is again by Professor Ramakumar, who says that as a principle in agriculture science, the future lies in creating new plant varieties and hybrids that are genetically tuned to withstand soil stresses. This is what transgenic science and new vistas like CRISPR technology aim at. Is that a real possibility?
Yes.
Oh,
And I would like to stop here. Yes, but then there are several other queries related to them. Then why we are not utilizing it? See, not transgenic. You know, there is some kind of politics and all other kinds of policy issues on use of transgenic. And I'm sure Dr. Bansal probably has given you a detailed deliberation on that, so I shall not go into that one. But if not transgenic, but high-yielding varieties, hybrids, and several other varieties and new cultivars are already in place. You know, in this country now, around 90% of, say, rice area, wheat area, or maize area is under high-yielding. Around 70% of vegetable are again high-yielding or hybrid. So farmers in this country, more than 70% or 75% of them, today they are using new hybrids, new varieties of higher yield with some kind of tolerance to biotic as well as abiotic stresses. So it is certainly going there. But had there been genome editing technology, CRISPR-Cas9 and molecular, particularly transgenics come as an agricultural scientist, certainly I would say yes, it should be. But then policy is policy. And whenever it comes, certainly we will be able to implement that. And I think I would certainly stop and not to comment much on that particular aspect. But certainly I would support the the new transgenic technology, new CRISPR-Cas technology, new genome editing technology.
Okay. Yes. Thank you for that answer. Very answer that was very to the point. But then you also deliberated upon the conditions of policy that perhaps science cannot directly have an impact on.
Yeah.
So we have a question. It's, Dr. Vivek Babu. He thanks you for your presentation and says that your presentation covered various nutrient status across decades, and you mentioned that nitrogen was deficient from 1950s on. I believe nitrogen from Indian soils was deficient from 1950s onwards. In that list, carbon or organic carbon is missing. If it is also missing, is it recent or since 1950s or since the beginning of farming?
Yeah. No, actually, in principle, plants take carbon as carbon dioxide from the atmosphere. So plant doesn't take carbon from soil. It takes carbon dioxide in atmosphere, and unfortunately or fortunately, we have sufficient amount of carbon dioxide in the atmosphere. Rather, it is increasing. So plants are going to be benefited. Yes, this is one of the benefits of global warming or enhanced concentration of carbon dioxide. So this is not limiting. Limiting are those which are available in soil and plants are harvesting year after year, and we are not supplementing or replacing those nutrients properly. So carbon or carbon dioxide doesn't come into that. So it is not limited. It is not having any deficiency. Rather, we have sufficient amount of carbon dioxide. And similar is the case for other two, hydrogen and oxygen, which are also taken up, not exactly, I mean, that water or it takes by root and then converted into hydrogen and oxygen and those kinds of things. So somehow these are not limited. Only the elements which are provided by soil, supplied by soil, and for which plants are exclusively depending on soil. So these are the nutrients, and those nutrients are like nitrogen, phosphorus, potassium, secondary nutrients, and microbes like iron, zinc, copper, molybdenum, and so on. Yeah.
Okay. So, Dr. Gopinath asks, can you please explain covering soil with crop residue, the technique? Yeah, if you could please throw some light on this.
That's it. Here the soil, say like rice straw, wheat straw, any other straw, any other.
Sir, may I request you to switch the video? Perhaps that will. There is some lag in your network. Dr. Pathak, can you hear?
Less temperature is going to be less. So that means less amount of water evaporated, you will be water, and you will be less amount of water. So this is number one benefit.
Nihira, can we do anything about it? No.
I'm just calling him 1 minute. Dr. Pathak, can you hear us?
Okay, we are just, for all of you, we have lost Dr. Pathak. There was some connectivity issue. Our online events team is trying to contact.
Am I audible now?
Yes, yes, sir. Yes.
Oh, sorry, I think there was some kind of disconnection.
Yeah, please.
So what I was talking about, that crop residue cover. So one.
Can you start from the beginning, sir?
Number one, it will be saving water because it will reduce the loss of moisture from the soil. Number two is crop residues also have nutrients and also like nitrogen, phosphorus, potassium, and also carbon. So carbon, of course, as I said earlier, that it will be taken up by the crop from the atmosphere, but carbon, when you put in the soil, it improves soil health, and organic carbon is very, very important component for deciding soil fertility or productivity. It improves soil physical properties, it improves soil biological properties, and so on. So this is the second one which you are going to see, the second benefit which you are going to get if you cover the soil with crop residues. Third one is the moderation of temperature, which is going to be another important factor because of global warming, increased temperature. If the temperature is moderated, so crop root will be growing well. So these are some of the benefits which generally we get by covering the soil with residues.
So, thank you, sir. So here's the last question for the day. Gautam asks, I think you have already dealt with this to some extent in your lecture. Maybe you can take some time to deliberate further on this. He asks, what are the key adaptation technologies that need to be focused in order to make Indian agriculture resilient to climate change, while simultaneously closing the yield gaps and increasing farmers' incomes?
Right. Number one, certainly I would say adoption of new yielding stress-tolerant varieties of every crop. Number two, technologies for water management, particularly avoiding flood irrigation, going to sprinkler and drip irrigation, or at least ridge and furrow method of irrigation. Number three, use of new fertilizer materials like neem-coated urea, nano urea, and if possible, going for fertigation. And then broadly conservation agriculture, which I was mentioning about maintaining soil cover with residues and so on. So these are just few examples, and detail I gave are the ones which will be giving lots of adaptation benefit to climate change to our crop production system.
Thank you, sir. So I think on this note, maybe I'll ask one question, lingering
Sure.
in my mind, and then we'll close the session. This is about, a lot. It was very insightful, and for all of us who are studying different disciplines and aspects of social science, a lot of this lecture and similar to the lecture by Dr. Bansal, it was very clarificatory in nature. A lot of sort of our apprehensions, to reuse the word, are being clarified as we go along with these lectures. So I was just thinking that, but general social science disciplines, there seems to be clearly an absence of these views, that what is meant by science-based policy making, and then how these kind of solutions do exist, and that also leads to that void, leads to us to look at some other kind of, say, traditional technologies, or as ZBNF and other technologies. So I was just thinking that what is the role of science communication, and enlightening the students who are not continue in the line of agriculture science, but are mostly into social science, students and scholars as well. So if you could throw your views on in that regard, and then we will close.
Yes, I shall not certainly go to blaming each other, but let me tell you why I use the term blaming, because I was thinking whether policymakers should come to the scientists or scientists should go to the policymakers. Who will come to whom to understand the reality? And probably both ways it should do. So a social scientist should come and discuss a person like me, what are the scientific aspects of abiotic stress management, climate change, what are the soil, water, and varietal kind of things, or I should go to a soil or a social scientist to explain, see, these are the things. Now, so leaving aside policy matters, I think science communication in this country, unfortunately, has remained little bit poor. So the responsibility is also with us. Partly, that doesn't mean that policymakers do not have any responsibility and we are solely to be blamed. That is certainly not the case. But as I said, I shall not comment on their part. I shall comment on my part rather. So probably we should be a little bit more communicative, talking to not only to scientists, but also to social scientists, to policymakers, to politicians, to explain the things. But at the end of the day, let it be 100% clear that if the policy is not backed by science, it is not going to succeed. It is certainly not going to succeed, whether it is in India or US or any other country. Only a science-backed policy can sustain, can give the benefit. Otherwise, it can continue for 1-2 years or something, or whatever. You can go on telling. It is not going to be productive. It is not going to be sustainable. It is not going to be beneficial to the farmers or to the country. So the basic thing is the policy must be based on science of physics, chemistry, biology, agriculture, and also social science. Also social science. Everything should be put together, and then only the policy should be developed. Now, who should reach to whom is an open question, and anybody can take a call on that one. But I said that our part, scientists' part, we are little poor in communication. Probably we cannot explain the things the way it should be understood by a policymaker or by another person, sometimes even by a farmer. So this is a problem. This is exclusively an area where some, other kind of trait or quality and expertise is required, and that's why we also discuss in our institute or in our scientific community that we have to improve this particular part, and we are trying our best to improve our communication skill, even sometimes some kind of training from a motivational speaker or so on. But then let's see how far we will be able to successful in this particular aspect. But this is an area which I fully agree with you, Mr. Bakshi, that science communication in this country should be improved. But then policymakers and social scientists also should make some effort to reach out to the scientists to understand the nitty-gritties of the system, the nitty-gritties of the science, because otherwise, for sure, it is not going to be successful. That's what it is.
Thank you, sir. That certainly is a note when we can end today's presentation. And maybe I'll take some pride that the Foundation for Agrarian Studies is at least taking some effort in expanding the base of communication.
I fully agree, and I compliment you and your team. I compliment you and your team for reaching out to us. And giving us an opportunity to talk to some of you, so that, and I do not know how much I have been successful in explaining some of the things. Had it been physical mode, probably the things could have been a little better. I would explain by some other ways also what I wanted to tell. But if I've been successful, at least communicating a part of the things which I was trying to do, I will be very, very happy. And thank you for taking this initiative, Mr. Bakshi. And of course your whole team, your whole team, Riya and others, whole team. I must thank Madam, because she was in touch with me for quite a few days, and I am extremely sorry. I am generally not a person who doesn't respond, but for last 7-8 days I am actually traveling. I am out of my office, and sometimes I am also in the areas where internet connectivity is either not existence or it is very, very poor. And sometimes some other meetings were going on. So I was not quick enough to respond back to you. And probably you had to write me a few more mails, for which I am extremely sorry. But certainly I'll be very, very happy to work with you and your team in future whenever you call me. And that will be another great occasion for me to again talk and discuss with you and your colleagues on some of these aspects of agricultural sciences. Thank you very much for giving me this opportunity. Thank you.
Sir, thanks a lot, and we look forward to more opportunities. Even
Can I request Dr. Ramkumar to say a few words?
Sorry, VKR, could you repeat that?
Dr. Ramkumar, did you want to say a few words?
Yeah, I just wanted to say a few words in appreciation of this lecture, as well as the way this whole lecture series has proceeded. One of the unappreciated facts in India's agricultural history, in recent agricultural history, is certainly the fact that agricultural scientists have, in National Agricultural Research System, have played a stellar role in upholding the principles of scientific temper, using science and technology to directly address people's needs, including food security, and also addressing different challenges in the field of agriculture, the farmers' fields, and so on. So one reason why the Foundation for Agrarian Studies, when we were thinking about this kind of a lecture series, one of the objectives was also to highlight this contribution made by the National Agricultural Research System to the improvement of agricultural science and technology in India. And I think all the lectures that we have had from Professor Rajendra Prasad, Professor Bansal, and now Professor Himanshu Pathak have shown that the role of the National Agricultural Research System in expanding agricultural growth in India, in addressing issues like food security, have been exemplary. So more on the one side, this was a part of communicating the benefits of science, but also it was also an effort. It was also our tribute to the system itself, in some sense, to highlight its contributions to the general public. The second important context here is the broad challenge that we face today, the challenges that scientific temper, rational thinking faces in the new era, where large numbers of irrational views masquerade as agricultural science or rational principles, and they are very, in a very major way, responsible for misleading general public opinion on the different challenges that we have and the solutions that are required to address them. So, some of these lectures have been very useful in clarifying some of the otherwise simple points, but which appears completely unappealing to the general public in some way or the other, but which for an agricultural scientist or somebody who has studied agricultural science is in some sense the ABC of their field. It appears completely unappealing to a section of the general public. So that's a distance probably that we need to consciously cover in this whole endeavor that we are into. And for example, a simple example of that you provided in your answer. For example, soil already has all the nutrients, and you only need to intermediate their availability to the soil. It's completely wrong to anybody who knows the ABC of agricultural science, but it's a view that is held by an extraordinary large number of people around us, including people who otherwise are supposed to think in progressive ways and so on. So your comments on science communication towards the end was also very important in that context, in the sense that we need to take the message of agricultural science to the common people, to farmers' organizations, and so on, who, through their demands and other activities, will be able to highlight them in the way they should appear or influence public policy in the near future. So I think Professor Pathak, your lecture was extraordinarily useful in serving that purpose, and we at the foundation look forward to your assistance, look forward to your support in our broad endeavor to take the message of science and technology to the larger public. So I must, on the part of the Foundation for Agrarian Studies, thank you for your contribution, and we are hoping that we will continue to have more such sessions in the future. Thank you very much.
Thank you, Professor Ramakumar. May I call upon Professor B.K. Ramachandran, Managing Trustee of the Foundation for Agrarian Studies, for a word of thanks.
It's a formal vote of thanks, but Ramkumar and Sandeepan have said all that I should have. I would have said, but thank you very much. This was apart from having enlightened us, having on the entire subject of abiotic stress. I think we can go away from this webinar with one additional mantra, that is, good policy doesn't come from bad science. So that's and we can say we can all of us can endorse that entirely.
Yes.
Thank you very much. Thank you very much. Thank you.
Thank you very much. It was,
Thank you
it
to
was
all
indeed
those
a
who
great
attended.
pleasure,
Thank you.
great occasion for me. Thank you very much. Yeah, thank you. Thank you.
Okay. With these words of thanks, we would now close the meeting. Thank you once again to one and all, to especially to Professor Pathak, all the panelists, and all of you who have been participating continuously throughout this series, and we hope to look forward to your participation in the next lecture as well. Thank you. Nihira, any announcement?
Our next lecture, which will be the last lecture in the series, will take place on November 27th at 4 p.m. again. So we look forward to seeing all of you there as well. Thank you.
Thank you very much. Thank you.
Thank you, sir. Thank you. Bye.